Shall we start? Okay. Hi, everybody. So I hope everybody is very no worries, everything's fine. So I hope everybody's energetic today. We are going to start RNN. So, yep. So we ended with the CNN and ResNet last time. So as I told you, you're now you have quite good amount of information to implement things which are like simple one-shot inference problems, like you want to do image segmentation, I don't know, any sort of classification or even regression problem. You can do it with the architectures you know. But what we want to talk from now on, it's a bit of more advanced thing, and that is RNN, so recurrent neural network. And that is the story about sequence data. So now we're getting a bit more advanced, and we're getting out of simple data sets with like one-shot input-output relation, and want to look into a bit of more advanced story. So RNN, you could consider it as a kind of bridge or a kind of start into the world of seg-to-seg models, which are nowadays like, for most of the applications you might have in mind, the advanced applications, they are the key components, okay? So even though in every lecture on deep learning or neural network, they are coming quite late, but they actually are quite older than many other architectures we have talked about. So 70s, 80s, people started to think about this, and they were unsuccessful, mainly because they couldn't learn everything through time. And then gradually, after they got back into the deep neural networks and they saw this is working, then they tried to get back on those architectures and see where the problem was. And they could come up with some interesting solutions. Some of them even existed a long time before, but at that time, people were not really looking into them. So let's start with the RNN. And the key factor in RNN is the fact that, as I told you, we are going to deal with sequence data. So what is a sequence data? So many applications, as I said, that you have in mind, many advanced applications of artificial intelligence nowadays we are thinking, deal with sequence data. All right? Like, for example, if you have speech data, like you want to do a speech recognition, you have a sequence of data, because your speech is a continuous sequence of words, for example, and these words are related to each other, right? So you can now think of it as independent sequence of data, which you can think of them as totally independent individual components or inputs. They are really sequences which have a sort of temporal correlation. Another thing is, for example, text data. When you look at the text, it's a sequence of words. Those words are related to each other. You do not write randomly words next to each other. They have a meaning, and based on some of them, you can predict what's going to come next, right? And also things like, for example, financial data. One of the very long story in artificial intelligence, and one of the most unsuccessful stories in artificial intelligence is financial data. That you look at, the trend of some financial records, like the price of gold, for quite some time, and you try your best to just collect as much information related as you can, and you want to give it into some machine which could predict what's going to be the price of gold tomorrow, right? So again, this is a sequence of data, right? So, and you have lots of other things, video processing. Sometimes if you want to just generate videos, frames next after each other, this is again a sequence of data, and you can come up with even more applications. So in these applications, there are 2 points that are somehow make trouble when we want to just use the classical MLP or CNN that we learned up to this point. The first one is that if I want to deal with that huge data, if I want to, for example, give a speech into a neural network, which is going to tell me what is the, I don't know, next word in this speech, or even it wants to recognize my speech. I mean, you listen to my talk and you want to know what I am talking about. Then if I want to do it with a simple MLP, for example, or CNN that we need to have a very huge neural network, right? Because I need to just fit all of my, say, 1 hour speech, 2 hour speech into that neural network as input, correct? So it's going to be a huge thing, which potentially you might think that, okay, this is going to be infeasible computationally. But there's one point here that intuitively, when you think about this, you do understand that you really do not need to have like the record of everything that I said during these 2 hours to find out that I am talking about neural networks, right? So you might have a sort of contradiction that even though computationally it looks to be a very complicated problem, a long speech given into a neural network to decide for the class of that speech, it sounds to be intuitively simple because, I mean, you really don't need everything in my speech. You just need to detect neural networks a couple of times, and then you understand that I am talking about something related to artificial intelligence, right? So these two things are the facts that made initially everything quite complicated to be tracked by classical neural networks that we had up to this point. So to just make it a bit more clear, let me start first with one simple example. So let's assume that you just get one 15-minute talk, okay? And you get this one, you want to understand, I mean, you listen to that talk, and then you want to decide whether this is about sport or science, okay? So for you as a human being, this is quite simple, right? So you really don't need to listen to the whole 15 minutes, right? So just a couple of seconds is enough probably for you to, or maybe a couple of minutes, first minutes, to understand what it is about. Now say that you want to train a neural network, which does the same thing for you, okay? Now, first of all, what kind of problem that is? That is a classification problem, right? Because you have input, which is that sequence of that speech, and then you want to classify whether this is science or sport, right? Okay. This is a classification problem. The data points are classified in one of those two classes. And what about the data? The data is a sequence, as I told you. So, like, if we want to be a bit, let's make it a bit more clear, more detailed. So say I have, this is the, time domain representation of my signal, so the amplitude of my signal, that has been recorded in analog form. So probably most of you do know how you deal with this issue, with such a signal on computer. So what you're going to do, you're going to just go and first sample this guy, right? So this is the typical frequency for sampling. So you're going to get for every second 44.1 thousand. So 44,100 samples, right, from each second. So very quickly you sample it. You collect those samples. Those samples are real numbers. You cannot save on your computer. The next thing that you are going to do is to quantize them. And now you have lots of samples, all of them quantized. You can save them on your computer, right? And this is how you have that 15 minutes as a data on your computer. The next thing that you are going to do, you are going to, it's a huge thing. So if it is 15 minutes, it could be lots of samples. Then you are going to just fix one frame size, right? Frame size n, say. And this is usually power of 2. And then you're going to just collect every bunch of samples into one frame. Now your input data is going to look like something like this, right? x1, x2 till some xt, correct? So this is your sequence of data in your speech. Each of them contain n different samples, yeah? And then each of these xt's is a vector of size n. Clear? Now, the thing that you are going to do, you are going to get this guy, and you want to just, out of this huge, sequence of vectors. You want to find out what is the class of this speech. You might even go ahead, compute FFT of those, frames and keep that in addition as extra information. I mean, you could do it. This is another approach. Or maybe you only keep the FFT. This is, depending on your application that you're doing. Okay, so now you have an idea about the data. For example, I mean, here is a 15 minutes. And if I assume that I'm doing really 44.1 kilohertz of sampling, then I'm going to have this much. It is almost 39 million, 40 million samples I'm going to have in this 15-minute stock. Okay? And say I use like a frame size 512. So I'm going to just make it into frames of 512, which is going to be around 78K different frames, right? So you have 78 different frames. Each of them is of length 512. Clear? Okay. Now, what should I do if I want to do the classification? Should I get this 40 million samples as a huge input and then give it into my neural network to just do one classification? So it's going to be a crazy thing, right? Because, I mean, even if I want to just use linear regression, linear classification, the logistic regression, like a simple neuron, a single neuron if I want to put there. Then I'm going to have 40 million different 4 to power, 4 times 10 to power 6, almost different weights that I should learn all of them, right? So this is huge. This is like close to some sort of, basic ResNet. You don't want to do that because you do know this is a very simple problem, But this is not the only issue. So one point is that you do know that there are some, simple words in this 15-minute talk. If you just listen to them, if you hear like 5-time basketball, soccer, I don't know, tennis, you do know that this is about sport, right? So you don't really need to train 40 million weights to do that. This is one point. So it seems to be some sort of unnecessary hardness for your application. And another point is that, I mean, it's very hard to generalize such a model, right? So if I have, so say I designed it for 15-minute talk. What if I want to classify 1-hour talk, right? What should I do then? Should I break it into 4 pieces and then classify every single piece? And then out of those pieces, I should do one extra conclusion? So this doesn't seem something like practical to be used in practice, right? So these are the 2 issues that you can simply see in this very simple problem. And there are a bunch of other applications. So one of the applications that we are going to use in this lecture quite a lot is this prediction of the next word in the text. So for example, say you have a sequence, a sentence. This is something that you already have on your cell phone. So when you're typing your message, at some point your cell phone is just suggesting you the next word, right? And then in this case, you are doing a prediction problem. For word prediction problem, we basically, I mean, in its deep down, we are doing a classification problem, right? Because we have it's huge, but a finite dictionary of words, and then we want to just select the next word. But many people call it prediction, And then what is, again, the problem? So problem is a sort of classification or prediction problem, which we want to find out what is the next outcome. And the type of data that I have is, again, a sequence of data. So I'm going to get the whole sentence, and then I'm going to just parse it into a sequence of words. Then I just represent every single word with its, basic representation, maybe ASCII code, whatever. So a bunch of numbers. Then I just fix the length of that frame for the word and put this number in that frame. And at the end of the day, I'm going to end up with the same thing as before. So a sequence of vectors, each of them with fixed size. And then I just want to know what is the next word, right? So this is going to be something like this. For example, this is a sentence I got last year from the U of T webpage. So U of T undergraduate student explore the use of AI to treat SP, and then what is the next, right? So nowadays, if I write it down, then immediately my cell phone going to say speech, right? And this is something like this. So you can think of every single word being represented by a vector of numbers, and then you have a bunch of vectors you got from first input or first vector up to vector t, which potentially t could be very large. And now you want to know what is xt plus 1, right? Clear? No. So again, this is a kind of problem that you deal with the sequence data. Other things, so as I told you, stock prices is the one. This is not the favorite one. I guess none of you is doing it for the project. I hope so, because as I said, this is one of the unsuccessful stories in AI. You really cannot predict the future of the market. But again, this is the same problem. Like you have a sequence of prices, and then you want to know, for example, what is the next outcome. Maybe you want to classify, you want to know it's going up or it's going down, or maybe you want to solve a regression problem. You really want to know what is the price, right? And then, again, you can just look at this daily prices as a sequence. You save them into form of frames, and then you collect those frames. You want to train based on them a predictor which gives you the next price, okay? So now the question, as I told you, I hope I could just root down in your mind that there is a problem here, and the problem is that we are dealing with a very, very long sequence, and we really don't need to go through the whole data at once, right? And want to find a way to go through this data in a more efficient way to do the job that we want to do, okay? So one thing that we always need in such problem is something of the form of a memory. So what does it mean? It means that, like when I want to predict the next word, somewhere in the sentence in between, there are words which are going to specify what's going to be the next word, right? And I need to have a sort of memory, that this memory is going to save those words somehow in order to be executed later on when I want to decide or predict for future. So I need a memory that could run over this sequence. This memory should have two properties. One of them is that it should be limited in size, because I have a limited size on my computer, and intuitively I do know that I really don't need too much of memory, right? The problem of, science sport classification, I just need to remember that I have heard lots of, sport stuff in that, right? So it doesn't need to be huge, infinite, but it should go infinitely in time back, right? So if somewhere long time ago I have talked about a sport, if it is necessary, I should be able to carry it out till this part of the time, right? So I need a memory. The memory should be potentially, or should impact potentially infinite, but I don't need, component that can potentially be finite. Sorry, this should be finite. I'm very sorry, this is a bad typo. So not infinite. So it should be finite. It should go infinitely in time, okay? So in time, it should impact infinitely before. Okay, so now let's look at this prediction of the next word, and let's maybe get a bit of more concrete example, which makes all of these stories I told you more clear. So say I have this sentence. So it's Julia has been nominated to receive Alexander von Humboldt Prize for, you want to choose the next word, okay? For the moment, let's think very simple, okay? Let's know that after for you want to put a pronoun, okay? What is important in this whole sentence to know? If I want to put the pronoun, I just need to know I'm talking about whom, right? If I know I'm talking about Julia, so I would say, okay, I just need to know that Julia is a single person female, so it's going to be her, right? So in this whole thing, there are lots of words here in between which are a part of sentence, but they are not really deciding for this part, her, for the next word. The only thing that is deciding for it is the person who I'm talking about, right? The red word. Okay, say we have this sentence and we want to decide for the next one. Now, for the moment, assume that we don't have any information on RNN, so we want to just use whatever we have learned to do the training for this guy. Okay? Now, how can I do it? Let's say that I start with making my data set clean. So I start with this sentence. I'm going for every single word. Like, for example, I look at Yulia. I just write those letters in form of ASCII words, ASCII codes. And then whatever left, I just leave it empty. And then I just keep it as a fixed frame, right? And then has been is, for example, the next word for me is again another frame, and so on till the end. So every single of these vectors that you see here, this is a vector of a fixed size, and say this is the vector of size n, right? So I can represent my data in this form. So I am going to represent my data in form of a sequence. Every single member of that sequence, every single entry is a vector of size n. And say I want to use one neural network to do this job for me. Okay? So I'm going to use one of the neural networks that you have learned up to this point. Okay? One neural network, it has some hidden layers, and now I want to train it. So let me just show everything compactly here for you. So at one particular time, this x here is one of the vectors in that sequence, one of the frames. Then I give it into my neural network. So it's going to go and pass over multiple layers, right? Hidden layers. So I'm going to put all of those hidden layers all together inside this yellow box. Okay? It passes over all of them. And then at the output, you get your final features. You pass it through your output layer, which is the red box. And then you're going to get your output. Clear? So it could be any neural network, as I told you. So green box is simply the input. Yellow box includes all the hidden layers. So it could be multiple layers. And then the red box is going to be your output layer. Clear? And anything, I mean, these arrows here, as well as anything inside this yellow box, they are all learnable, right? So there are a bunch of ways that you are going to train. You're going to just optimize by minimizing your loss. OK, great. So one example is, for example, if I have one MLP. So this is my input. So I put every single number in my input vector in my frame on these green nodes. And then it's going to pass over those fully connected layers, right? Just get multiplied with the weight, go for the next hidden layer, gets activated, go for the next one, and so on, till you get to your output. Clear? Great. Now, what I do need for this problem, in my problem, I am doing the text prediction, right? And I told you that I'm showing every single word with a fixed frame. So this means that if my input has n, size n, my output is going to have again size n, right? Because my output is the next word, correct? So I give one frame to it, which is the very last frame, for example. And now I want to see the next output, which is the next word. Correct? OK, so here what I'm going to do, say, for example, I'm just using a simple MLP, fully connected neural network. And this guy is going to get one single frame as the input. So it is of size n. One of, for example, in this speech example, it is that 512 different samples are going into this layer. And then you're going to pass over all of those hidden layers. And then at the output, I am again having n different samples, right? Where these n different samples are specifying the next word for me. Clear? Everybody's clear what I'm doing? Great. Now, what I want to do, I want to just train this MLP, meaning that I want to just know all of these weights here and weights inside the hidden layer to be specified. And how can I do it? Say I have just one sequence. How can I do it? Any suggestion? Any idea? How can I train? How can I make data out of that sequence? Sorry? Yes, but if you want to train something, you need your, since you do know, for the moment, you just know supervised learning. What do you need to have? You need to have a bunch of data points, right? So you need to have a bunch of pairs of input outputs, correct? Now, if you look at your sequence, how do you make that? Subsequenting words, exactly. Yes, exactly. For every frame, you're going to look at, you give every frame as the input to your neural network. Then you set the label to be the next word, the next frame, right? And you make your neural network to get the first frame, first word, gives you the next word, right? Then you're going to give the next word to it and train it to give you the word after. And you keep on doing, and then at the very end, you hope that if you give the last word, it's going to give you the correct next word, okay? So let's look at it together. So the thing that I'm going to do, I'm going to put here xt minus 6, for example, so the word Julia. I'm going to give it here, and then it's going to pass through that neural network. At the very output, I put the label to be xt minus 5, correct? So I'm going to make this neural network, train it to give me the next word. Clear? So it's going to get trained so that when I give Julia to it, then it's going to give me at the output has been, for example. Clear? Now, I'm going one time step forward. Now, the next frame is has been, for example. I'm training to give me as the output nominated to. Okay? And I keep on doing like this, right? So nominated to, then I want to make it receive. Give me output receive. I give receive to it. I wanted the output Alexander. Alexander von Humboldt. And then prize 4, for example, is given as the input. And now I hope that in this part, it's going to give me as the output her. But what is your prediction? Do you think that it's going to give me her? What do you think? It's not, of course. But why you don't think that it's going to do that?
There's a million words that in the vocabulary that you can pick from. So her, it's very low likely.
Yes. There is no reason for your neural network to remember that you're talking about Julia at this point, right?
Yes.
Because you just made it to say after Julia has been, right? Which is, somehow related because Julia is a single person, it should be has been, but it doesn't connect Julia to this word at all, right? So your neural network is not really remember that you're talking about Julia. Because the moment you get here, it's somehow totally changing training towards the case that for the previous word, it's going to give you the next word. So it's going to give you prize, and after prize 4, there is no reason that this neural network is going to learn her, yeah? So you're not really connecting her, the next word that you're looking for, to the right spot in the sentence, in the sequence, in this sequence to find out that the next word is going to be her, okay? Even if, like by geniated information, it's given to your neural network that it's going to be a pronoun, it's not trained to just find out whether it is her, his, their. It cannot say. Yeah? Everybody's clear? So this is an issue. It cannot really remember what we are talking about. And this is the key challenge that I was talking about, the memory. Okay? So your neural network, your MLP, is simply trained to forget what has happened before every time that you are training it for the next word. Yeah? And you might say, okay, at some point of time I was talking about Julia, so there is some part of Julia inside this training. Of course, but you didn't label Julia with anything in future. You just label Julia with the next word, which was has been, right? And also your, for example, neural network has been trained to just give after nominated to the word receive, which is totally irrelevant to what you're looking for. Clear? So now the point, yeah, as I said, so when you get into this word X, you hardly can connect your output to the input Julia. And this is the point which I was talking about. So you really need to have a sort of memory inside your neural network which could capture this fact that you are talking about one single person female, so that at this point it is able to just give you some meaningful output. Okay? Well, you might say, okay, maybe I can just extend the inputs, right? Okay, if I just make the input very, very large, then Julia is going to show up somewhere in the input, and then hopefully it's going to train well to just give me the word her at the output, right? So it means that you want to just go over the whole thing up to Julia in order to get the output somehow impacted by the word Julia, right? So Julia is now included in the whole thing, so the output could be potentially her. That's right, but if you want to do it, just think about the case where Julia has happened a couple of pages ago, right? Then this is impossible for you really to make such a neural network, because then you need a super giant neural network which gets the whole text into it and then could just predict the next word, which doesn't seem to be feasible, right? Even with the computers we have nowadays. Yeah? So this is not really the case. So we cannot really use MLP, like basic feed-forward neural networks that we learned in chapter 2. So you might say, okay, maybe we could just get the idea from convolutional neural networks, right? So in convolutional neural networks, we had convolution, right? And that convolution helped us to deal with a giant input with a small number of weights, yeah? So we had this idea of convolving, so we get a filter, we just slide it over the input, and then we capture the information from that input. That was the idea. In your assignment, you did the one-dimensional case, where you get a vector as the input, and then you just get a filter, you pass it through that vector, right? Slide it over that one, and that filter is small, but it can just scroll over the whole vector, right? So maybe this is a better idea. So maybe I can get one filter here. So here, as you can see, I have this green thing. The green box is actually the larger window of inputs that I'm taking, but I'm not processing all of them with different weights as we do in MLP. I just put one smaller filter of size n, and then I scroll it over that input, right? Maybe I can do that. Maybe that's going to help better, right? So at least I'm not making it giantly large in terms of number of weights. Yeah? So maybe I can do that. So I'm going to have one CNN. So I fixed the filter size to be n. So the filter size is now exactly the size of one frame. But I just scan a larger portion of my sequence as the input. And then out of that, I'm going to just talk about the future. Okay? So what's going to happen if I do that? So for example, if I am at time xt minus 4, I get that filter, that blue box. I first put it on xt minus 6. I just do the linear operation. I collect some features. Then I scroll it next, xt minus 5. Scroll it next, xt minus 4. And then I collect those features. Then I post-process those features in my hidden layers up to the point that I get my output, right? Clear? And then I just go for the next time. So when I come to time t minus 3, I'm going to start from t minus 5. I do the convolution up to this point. Again, I predict the future. So every time I want to talk about the future, I don't look at just the previous time frame. I just look at 3 previous time frames. And I just get a kind of collection out of them, process them, and then try to talk about the future. Okay? Now, if I keep on doing like this guy still cannot talk about, it cannot tell me that the next word is her, because within the frame that I am, or the hyperframe that I am scanning at the input of the CNN, I don't have the right word, the word Julia, right? So How can I deal with that? How can I resolve that issue? If I want Julia to show up here, just you need to start from very beginning and scan everything, right? Yeah. So I need to just send this guy to be infinitely large again. I'm not increasing the number of weights that I have. That's a good thing. But the issue is that it's going to take forever, right? Every time I want to talk, I need to wait till this filter starts from very beginning of the text and just scrolls over everything and captures all the features and then give it to me, and then I can talk about the future. And this is with this assumption that all of it is going to work fine, which is going to be a bit hard to believe because there are lots of irrelevant information in between. So if I want it to really work fine, I need to have a very deep CNN. Yeah? But again, I get into the trouble with memory. Yeah? So the issue here, as I said, is that both of these architectures, the MLP and CNN, both of them have a sort of thing that we call it finite impact memory, meaning that any of CNN or MLP architectures, when you give an input, it's going to learn from that particular input to connect it to the particular output, right? But it doesn't learn about any connection between this input and another input, because you basically give everything independently to that neural network, right? So they are going to remember only the things that are inside their inputs, because those inputs are given to them independently, and they are not looking into any correlation between different kinds of inputs. And what we need here when we are dealing with a sequence, we really need to learn this sort of temporal correlation. So we want to understand the connection between every frame inside this sequence, which is not going to be captured by any of those architectures, right? So one thing is that if I want to really remember for a very long time, so as you saw in those architecture, you need to have this kind of huge input, right? Because you do know that you can remember only from the input. So if you want to have infinite impact memory, you really need to have infinite input. But from this example, this naive example that I showed you, you really, or intuitively, you know that for this application, you don't really need infinite size memory. Because what you only need to remember is Julia, right? Just you need to know that you're talking about Julia, and then everything is over. So the size of memory component is fixed. It's only Julia, yeah? But it could happen anywhere in time. So your memory should just carry everything backwards towards very beginning, right? So this is the idea that we say. So this is the component actually that we're missing in those architectures that we had up to this point. And that is a sort of memory component that is finite in size. So the size of that memory, I can just save it on a small portion of my storage, but it could just be influenced infinitely. Yeah? I mean, of course, in practice, infinite doesn't make sense, does not have a meaning, but theoretically it could go forever, right? So, did you get the idea what I'm talking about? So what we are missing here? Now, yeah, sorry? Yes, a kind of moving average stuff, exactly. Yeah, somehow, yes. Great. Any questions? Cool. Now, have you ever heard of state space models? Anyone had anything on control theory? State machine is the same thing, yes? Yeah. So these are the guys who are going to help us make that component. Yeah? So what is that? Let me just talk about this guy. So say I have one system, yeah, one box. It's going to get X as the input. It's going to give you Y as the output at every single time. And in addition to that Y, it's going to give you something called state of your machine. At time t, I have state st, right? Now, the next output of this machine is going to be yt plus 1 and st plus 1, which is being influenced by the new input xt plus 1 and the previous state st. Clear? So you have your box. You get your box, which is, this is your system, whatever it is. So this is your model, for example. And then you're giving to it this xt as the input, and you get yt. This is what we had up to this point with conventional neural networks that we had, those feed-forward neural networks. But now, what if this guy is giving me some state, and each time I'm just connecting it backward to my, giving it as a feedback to my system? Yeah? Then potentially, this state guy is going to help me keep track of everything happening through time, but with finite size, right? Because I don't need to make it infinitely large. I'm just updating it every time, right? So this is what we call it a state space model. So this is a kind of model which depends on the state. And the key point about the state is that this is a finite size variable, and then it could go infinitely large in the time. Okay? To just see this idea, let's just play around with our neural network and just add a state into it. So what I'm going to do, I'm going to get my neural network that we had. So this, So this neural network that we have, for example, the MLP that we had before, it was getting one frame as the input, then it just passed it through the hidden layers and give me the output frame, correct? Now, let's modify this neural network so that in addition to the output y, it's going to give me also one output s, okay? This s is a new output, right? So for example, if I want to have, say, I mean, this is not a big deal for you, right? If you have a MLP, you can simply just, I mean, say you had MLP, so you had xt as the input, and then it was going through multiple layers, and then at the output you had this layer which is now of some specific size, say for example n, and this is yt that you get it. So you're going to add a bunch of other neurons at the output, right? And then you call these guys to be st, correct? And then you connect all of these weights, all of these neurons with some weights to your previous layers. You can make it simply larger at the output, correct? So say we do that. So now in addition to the yt that I have, I'm going to get some sort of st. Now this state, after each time with some delay, I'm going to feed it again to my input. Meaning that, for example, I'm going to get this guy, and then I add it up to this input here, for example, right? So I just add it up to my input, and then I try to go for the next time step. So what's going to happen if I do that? For example, I usually start with some initial state. So say we agree on one as 0. This is the initial state. Then the next output y1 is going to be a function of that S0, the initial state, and your first input x1. And then when you get y1, you're also going to get your first state, right? You keep that state, you give it with x to your neural network again, and then you're going to get y2 and s2, right? And you keep on going like that in time. Clear? Now, why this is going to be infinitely long in time? Because, for example, I assume that I start with some s0, and then I just give x1, so I have only input at time frame 1. Okay? I only give x1, and after that, I stop giving any input to my neural network. Yeah? So x2 and anything after that is simply 0. What's going to happen if I am at particular time t? At time t, your yt is going to depend on your xt and st minus 1, correct? But you don't have any xt, right? I told you you just give x1. Xt is 0. So it's going to only depend on st minus 1, right? Now, what about st minus 1? It was the output in the previous time, right? With yt minus 1. They both came in the previous time frame. And st minus 1 was depending on xt minus 1 and st minus 2, correct? But xt minus 1 was again 0, all right? So it was depending only on st minus 2. So yt depends on st minus 1, st minus 1 depends on st minus 2, and you can keep on going like this till you get to the very, very beginning of time where you have s1, and that s1 was a function of x1, correct? So you give x1 at the beginning of time, you stop giving anything to this neural network, but if time goes on, this neural network is going to generate some output which is depending still on your x1, right? And this is simply because you are carrying that x1 in your state. Clear? So it is going infinitely back in time, but you don't really need to have infinite size because st is fixed. Right? Question?
For example, if we consider a sentence and we are predicting the next word, I was wondering, the next word is a YT, and what is ST exactly in this example?
We are going to talk about this. So we are going to have models.
Yeah,
so
another thing which comes to my mind is that, for example, if we didn't have this ST2, for example, if we predict X2, it's still dependent on X1. And also we can tell if we have an XT, it's dependent on XT minus 1 and X.
of course. But you are carrying all the information, right? So your yt, it does not only depend on your xt, it depends on xt minus 1, xt minus 2, xt minus 3, till x minus infinity, right? And that is the thing that you wanted, right? Because you want to capture word Julia anywhere in the sentence.
Yeah, but I think that there is, I cannot find any more positive point to having this ST. You know?
Because, say, if you remember this example that we had, this, I think I need to go very back in. So if I have this example here, this example, yeah. So if I have so here what I'm doing, here I'm giving this xt minus 6, I get one output, right? The next one, when I'm giving it into my neural network, the output only depends on this guy, right? It doesn't depend anymore on this guy.
But if we consider the output, for example, in this one, we consider the output as xt minus 4.
Yes.
Yeah, it would be.
And then your neural network somehow learns to make a coherent sentence, right? So it doesn't only learn to have after has been being nominated, it also learns that it should talk about someone, right? Julia has been nominated, right? So it's carrying information from that point of time. So when you get here at this point, this state, which is a memory of your neural network, is going to carry some information about every single word before it, right? And I mean, it might sound a bit complicated to you, but we are going to make our best to make it work. That it's going to find out Julia was the important thing, then it's going to put her after that, okay? But if you don't have any impact of this word Julia at this point of time, you cannot do anything, right? At this point, we have something. Your question is how we can make it work. I mean, we are going, backpropagation is going to make it work, right? But at the end of the day, you need to carry that information through time. Yeah? So, everybody clear about what we're doing here? I mean, I don't expect, I mean, these are mostly apple and banana things. Like, I'm just giving you the, intuitive idea behind it, but then we get into the nice parts, including backpropagation part. But at this point of time, I hope that it makes it clear for you that we are just, this kind of recursion inside our neural network is mainly aiming to make a sort of memory, which is passing through time. And you might say this is infinite in time. I would say this is exactly what I want, right? Because I want to capture everything inside my sequence, right? Because I do know that my sequence contains a sort of finite memory for what the task that I'm doing. Clear? Any questions? No question?
So the backpropagation will depend on the first x1 value.
No, it depends on the whole time slot. So it's going to be a very, I mean, initially people stop working on it simply because of backpropagation. You cannot simply backpropagate, but then you find out a way to do it. Yeah. So no, you actually need to backpropagate at every single time all the way back to the beginning of time, which is a very hard thing. And your gradient easily vanishes. So, yeah. Okay. But for the moment, you don't need to think about, I mean, we talk about the training. Don't think about the trainings. Just want to make it clear that we need a memory, and we can only make it by making this state. Okay, so now, this state space model, like carrying a state or incorporating a state inside our model, this is a good idea. It's going to resolve the issue. It's going to make us the memory component that we are looking for. But there are lots of challenges for making a kind of, a good state-dependent neural network. This is a kind of challenging thing. And you might tell me, okay, what kind of challenge it could be? I mean, just instead of having x mapping to y, just make x as x and state mapping to y and s prime, y and next state, right? Just do that mapping, and then put lots of weights, other things, and let it train. Yeah, it might sound initially very simple, but the issue is that it's quite hard to find the right choice of state and exactly to learn to find out how you can really learn from that state to keep the record of what you want in the sequence. So the key issues are, one of them is how we can exactly define the state variable. So I think it partially addresses the question you asked already. So you don't really know what is that state, right? You do know a state is a good thing, but what is that state, right? You don't know that. And another thing is that when you're training neural network over the time, so when you are passing over this sequence, everything inside your neural network is going to change, if you're training, every time step that you go forward, right? So if I am at this time, now I'm just making my neural network to put the next word, and then I go next time, and then I want to just modify everything in between to just make the word after, right? And then this means that changing everything inside this neural network not only going to change my performance or my prediction for the next word, but it is also impacting my previous training, which was to get one word and generate the next word, right? So, as I said, I don't expect you to follow me exactly. This is what this whole chapter is about. So we are going to break it through. But I hope that you got the key ideas. So the issue is how we define state and how we train that kind of state-dependent neural network. These two things are very challenging, and the whole chapter is about making these things happening, okay? Okay, so now, yeah, maybe I can give you 5 minutes. So this story is pretty much over. Now we start with a bit of more math. So 5 minutes and then we start. Okay, shall we go on? Okay, great. So, yeah. So the two main challenges, as I told you, the first one, what is the good state, how we can define it. The second one is that how we can train it, how we can train a recurrent neural network to remember things from the sequence. So there have been lots of trials. As I told you, this story started long before. And as you might know, one of the key area or domains that we use RNN, or more generally seq-to-seq models, is the natural language processing. And people who started thinking about this were people who were working on linguistic. Like many of them were thinking, can we design a machine which starts to just say coherent words, like after every single word it just gives another word which is related to the previous one, right? So this started quite early. So Michael Jordan, not the basketball player, he's a professor at the CS department in Berkeley University. So, and he is still active. So he gives time to time plenary talks in several conferences. So he came up with one idea, one very basic idea, which people still call it Jordan network. So his idea was to get the output, simply average it through time, and then consider it as a state and give it back to the neural network. So this was the most basic one. And there was also Elman network. So Jeffrey Elman was a professor at UC San Diego, and he passed away in 2018. So he was a linguistic guy. So he actually studied something between psychology and neural science. And his main contribution was to design a machine which would start to talk about like human being. So he came up with a better idea. So 4 years after Jordan, he just came up with this idea that maybe we can just make a better state. They were like the simple form of what we nowadays know as recurrent neural network. Yeah? So the recurrent neural network is simply a kind of neural network which is state dependent. So it's going to compute some state at every single time, and then it's going to just get it back to the input of the neural network to decide for computing the next output of the neural network in the next time slot. Okay? So RNN, if I just want to define it very basically, is the term for recurrent. It just says recurrent neural network, and this recurrent simply refers to this connection that is just computing the state and giving it as the input again to your neural network. Okay? So these two things are the ones which people call them sometimes sRNN, simple RNN. And they were like first stories, first attempts, and then they got forgotten up to the point when people again started to deal with the neural networks. So let's look at Jordan network. So if we look at these two models, we're going to get the idea of where the trouble is when we want to just use this state and when we want to learn from that state. So in the Jordan network, the idea was that once you compute, like if you give one frame as the input into your neural network, and say that you just pass it through multiple layers. In the original proposal, it was a simple, shallow MLP. So this green box was just a single, fully connected layer. And then at the output of this guy, you compute one hidden vector of hidden features, which you give it to your output layer. Okay? Just simple, shallow, feed-forward neural network with one fully connected hidden layer. Okay? So the idea was that once you compute for xt, once you compute your output, then you're going to just compute a kind of moving average on that output, and then you keep it as your state. And in the next time interval, you're going to give this state as one extra input to your hidden layer, so together with your input. So if you want to just write it down mathematically, what does it mean? So it means that if you're at particular time t, your state at time t is going to be the state that you already had. So you start with one initial state, say for example 0. Then at every single time, you're going to get your previous state, multiply it with mu, and then you add it up with the new output, right? So you start, for example, with S0. So, okay. You're going to start with some S0, and then you're going to give x1. So say I put s0 to be 0, then I'm going to give x1. If I give x1, if s0 is 0, then my next s is not going to depend on this s0 is going to be 0, right? So s1 is going to simply be mu times s0, which I put at 0, plus I give x1 and I get y1, right? Correct? And then for the next time, so s2, when I want to compute it, it's going to be mu times s1 plus y2, right? And then, of course, you can just replace this s1 with y1, correct? So it's going to be y1. And then you keep on going like this, right? So this whole thing going to be s2, then your s3 is going to be mu times this guy times s2. This is not, no, this is better. So plus y3, correct? Sorry? Here, no. Look. Oh, sorry. You're right. But no, then I think I've done some sort of mistake. I guess I've done some mistake. I think it should be S1, Y1, YT. So let me just, okay, let me make sure. So y2 is s1, which is x1, and then, okay, you're right, I guess. So then you mean that here it should be y0, which doesn't make sense. So I should basically start from s2, you mean. Okay, so s2 is going to be mu times s1. Okay, plus y1. You're right. Sorry. And then I assume that s1 is simply 0. Thanks. Yeah, I think this is the point. S1, I think I changed the indices. I hope that I have not done any mistake. It's working, I think. Now, no, it shouldn't be 0. We talked about this. Yeah, you just agree on one initial state. Just for simplicity, I put it 0 right now. Okay. Yeah. Sorry? Index in time? I mean, it's your choice. I think I changed it to just make it starting from 1. Yeah. So I hope that I've not done any mistake. But yeah, I just wanted to make it like start from 1. So I put the initial state to be 0. Then the next state is going to be computed like this. If this is 0, then this is going to be simply y1. And then you keep on going like this. So your s2 is going to be mu times y. Your s3, sorry, is going to be mu times y1, yeah, plus y2, and then s4 is going to be mu times s3 plus y3, and so on, right? So each time you just get your new output, and then you delay it with time. I think I'm right. So I just do a delay. I just add it up, do this moving average, and then I compute the new state. Okay? So once I have the output at every single time, I can update my memory. So Jordan calls this memory to be context. Yeah? So this ST for him is what he calls it, context. Okay? And now, what it's going to do with this context, it is going to pass it through one linear layer and add it up to the original transform input, and then it activates it, right? So it has one linear layer, which gets input x1. It has one other separate linear layer, which gets as the input this state or this context, and then it adds them up, as you can see. And after all of it, it's going to activate it, so it's going to compute the output of the hidden layer. Clear? And now that you have the hidden layer, everything is as before. So you're going to get that hidden features, and then you again multiply with a bunch of weights, and again you activate it. It's going to be your output. Clear? Everybody's clear what we're doing here? So this state, this ST, or context, potentially could just go backward to the very first input, because the first input is going to impact Y1, so it's going to impact S2 as well, and then this is going to show up again here, so I think I should have written here S2, so I did a bad mess here, S2. Yeah, this S2 is going to show up here, and then this Y2 is going to depend on X2, so everything now depends on X1 and X2, right? And then you're going to carry out here, and then this guy comes here. Now Y3 depends on X3, so you have something at time 4 which depends on X1, X2, X3, right? And you keep on going like this in time, yeah? So you potentially, at every single time that you're computing your output, you're computing something that relates to the very beginning of time till now. Yeah? Clear? OK. So now this is the same story that I told you here. So if you, for example, set the initial state to be 0, and you only give x1 to your neural network, then your first output is going to be simply this guy. So it only depends on x1. Then your second output is going to depend on your state and your y1. So I told you the initial state is going to be 0, so forget about that state. So only y1 going to show up. So this guy is 0, as we have here. And then your next state is going to be your previous output. So now what you're going to have, your previous output is again depending on your previous input x1, so your y2 is going to depend on your previous input, right? And if you don't even give any input after x1, every single output that your neural network generates depends on that x1, right? But it is not depending very easily on that, yeah? It's going to get more and more nested. Clear? You got the idea? So that was the idea of Jordan. What Jordan did, in Jordan model here, what he thought that this Wm, W1, and W2 are some weights that you can learn, meaning that you're going to start with some initial values, you're going to go over a bunch of sequences, and you try to update them by gradient descent, such that you're going to minimize the empirical loss, empirical risk, right? Fine. But he didn't really do it in depth. Yeah? He didn't really do it completely. So the issue that was that in his model, he couldn't really explicitly learn them. He somehow did it implicitly. And I'm going to show you very quickly after the Elman model what the issue is here. But if we want to talk very high level about the Jordan model, the main issues about the Jordan models are these two things. First of all, he is finding some sort of memory component, but this memory component is a sort of predefined component. So he doesn't say like, OK, I have a general S and I want to learn it. He doesn't say that. He says like, state is simply moving average of the output. But the question is why this is a good idea, right? Who knows? So it was just an initial try. And the other thing is that since this state is not defined explicitly, he has no way to just learn how to remember things from before. The only thing that he can do is to just learn this WM, which basically just tell you how you can use your memory, right? He doesn't really learn how to remember. He only learns how to use the memory, which is still fine. It's better than having no memory, but it's not what we want exactly, okay? Moral of the story, this guy was not working. I mean, when you just do the training, it's just going to collapse. Yeah? Then after that one was 4 years later, it was Elman, and Elman got this idea that maybe it is a better idea to go for the hidden feature. And why we need to go for the hidden feature? Do you have any idea why going for hidden feature, hidden state, what we call it hidden state, this hidden layer output is a better idea as compared to the output?
Because it contains more features, like theoretically it contains more features, that's more information than our output.
Because it's
Yeah.
learnable.
It's learnable, great, yeah? because it's learnable, as your friend said. I mean, maybe you are intuitively saying the same thing, but this is a key point. Yeah? When you are making your neural network, if you do have the label, what you're going to do at the end of the day? You're going to make your output to be exactly that label, right? You want to make your output to be the label that you do know when you are training, correct? So when I am training a classifier, I give image of cat, and I make my neural network to tell me this is cat, right? Then I give a dog, and I make it to tell me that this is a dog, and I hope that in future, whatever cat or dog I give to this neural network, it's going to predict it right, correct? So that output, I'm going to make it to be exactly the label that I do have. But for the hidden feature, the hidden layer, this guy, I do not have to make it anything specific, correct? I just leave it learn, right? Leave it learn what features are inside my image. And then this was the idea by Elman, so maybe it is a better idea that we just work with this guy. And he did it very simple. So he said, like, state at every single time is the output of the hidden layer in the previous time. Now, it's still a kind of memory component, because every single time you're carrying everything from before. But now you have a hidden state or hidden layer, which you are not imposing any specific behavior on that, right? You don't care if your hidden values are large or small. Some of them are 0, some of them are non-zero. You don't care about it. The thing that you care about is that your output is the right output, right? And maybe this is a better idea. You have more degrees of freedom. So he did the same thing. The rest of it was exactly the Jordan model. The only difference was that he just changed the definition of state with this intuition that now I can learn that state. Yeah? I can learn that memory. And yeah, you just give your input and your state through linear layers, and then you add them up, and then you activate them, and after that you're going to just compute your output by a fully connected layer. Right? Yes?
Sorry, we need a memory for the state. How much are?
This state is your memory. You need a memory to just capture the temporal connection in your input.
And for example, how long can we keep the tags and something like that?
This is the point. I mean, even a more advanced idea is not going to work immediately. This is why we introduced a thing like gating. And this is the point where it's going to work. But we're just doing the very small, the basic ideas. So we're going to build based on that. No. But it's a hard thing. Really, it's a hard thing. No. So RNNs are known to be one of the worst things when you want to train them. But after a gating idea, they start to work. Okay. Everybody's clear? So this was one step forward. So again, you can just say, like, I am just putting 0 initial hidden state, and meaning that I have 0 initial state, and after that I just put 1 x1 as the input, but then everything in future going to depend on x1, meaning that I'm capturing the memory through time, right? But again, I mean, Elman was one step ahead, because he was now just taking something as a memory, which was learnable as compared to what Jordan did. But again, he did it implicitly, so he didn't learn really explicitly. And I know that you are really annoyed with this whole, generic explanation. Since you are very interested on that, I'm going to show you one tiny bit of backpropagation issue that at that point of time they couldn't do. And then I'm pretty sure, even though you're going to hate me because of backpropagation, you're going to find out what I exactly mean by learning it explicitly. So both of these Jordan and Elman networks, as I told you, they had the memory, but the issue was that they could not really learn it through time. Yeah? And this is the key challenge that we do have. So we cannot simply learn through time. And if you want to understand what is happening here, let's just consider, a high-level example. So say I have a sequence of length t, and I'm giving it into Elman. I think I considered Elman case, right? Let's see. It doesn't matter really. So yes, I think I did the Elman model. So say that I have a sequence of inputs, so x1 to xt. This is my data sequence. And what I want to do, I want to just train the Elman model that we had right now on this particular sequence, okay? And for simplicity, say that I do know what is the required label for every single time. Meaning that I do know that for example, x1, I need to have label v1, x2, I need to have v2, and so on. This is not necessarily the case. This is a part of this section, so it is a one-to-one issue that we might have. But for the moment, say that we do know what that is, right? And then what I want to do, I want to just make my neural network so that every single time it's going to give me yt, which is exactly the label that I want. So I'm going to compute the difference between label at time t and the output at time t. I sum them up, and the thing that I want to just minimize this kind of loss, right? So by doing that, I make sure that my neural network is giving me at every single time the output that I want. Clear? Now, the first thing that I'm going to do for you, just a warm-up, we're going to use the Elman network, but we don't have any memory. So basic MLP, a shallow MLP, meaning that every single input, xt, every single entry in my sequence is going to be given to my neural network. I compute the output of the hidden layer, and then I just pass it to my output, which gives me yt, right? There is no memory element here, right? And then what is going to happen? I mean, I'm going to compute this ht in this form. If I assume this is Elman model, this is simply a fully connected layer. This guy, again, is a fully connected layer. So w1 is the weight for this layer. w2 is the weight for the next layer. And then that's going to be my output. Clear? OK. So if I want to compute, for example, if I want to just train this model, what I should do, I start with one w1 and w2, right? And then I go over this whole sequence. I compute that loss. And once I computed that loss, that average or sum loss over time, I'm going to compute the gradient of that loss with respect to w1 and w2. And then I just subtract it from my current weight, right? And then I repeat this over and over till I get to the stationary point. I know that I am over with optimization. Clear? OK. At the end of the story, I need to compute these two gradients, right? And as we all know, the only way that I can do it is to just backpropagate. Clear? Just use chain rule over and over. OK. Now, if I want to just make it in a diagram for it, so it means that I have this sequence starting from x1 to xt, and every single time frame or every single entry of this sequence is going through this network, I get a particular output, and then I'm going to compute that loss between this guy and the corresponding label, correct? So between these two guys. And then the thing that I want to compute is the gradient of this sum loss with respect to any of those weights. Clear? OK. So now, if I want to do that, I can start by doing, just a bit of notation. I'm going to write this r hat t. I simply mean that the loss at particular time t. And my total loss is going to be sum of those losses at time t, right? And now the thing that I want to do, I want to compute the gradient of every single of them with respect to one of the weights, for example, w1, right? So if I want to do that, I'm going to use chain rule, right? Like what we did before. And I'm going to use the cheating approach, so I'm not going to open it up in terms of the entries anymore. But I think after lots of practices we had, you have the idea. So what I'm going to do, I'm going to say, for example, I want to compute the gradient of r hat t, a particular time t, with respect to w1. Then let's look at r hat t. So say r hat t, we said that this guy is the loss between yt and the label vt. So if I want to just compute the gradient of this guy with respect to any weight, the first gradient that I should do is with respect to the output, gradient of loss with respect to output y, right? So say I want to compute the gradient with respect to w1 of r hat t. Now if I write the chain rule, what should I write? I would say gradient of r hat t with respect to yt, correct? Times, so I'm going to use this general form of multiplication, times what? What is the next thing? Gradient of yt with respect to w1, correct? So it's going to be gradient of yt with respect to w1. Clear. So this is what we have there, right? So gradient of my loss with respect to output at time t times gradient of output at time t with respect to w1. Okay? Now, next thing, if I want to compute the gradient, I do have this guy. This is just a gradient of the loss function. I need to compute this guy. If I want to do that, what should I do? So my yt, what is it? Yt, I told you this is the activated version of w2 times ht. So what should I do? Again, the chain rule. So gradient of yt with respect to w1 is going to be the gradient of this guy with respect to first what? w2 is not showing up. It's a constant in terms of, it's going to be 0, right? Gradient of w2 with respect to w1 is 0. I want to compute gradient of yt with respect to w1. What should I write? It's going to be the gradient of what? Yt first, of course, with respect to ht, exactly, times gradient of ht with respect to w1. w1 is going to be in ht because ht is computed out of input with respect to with w1, right? You could write gradient of y with respect to w2 times gradient of w2 with respect to w1, but the second one is going to be 0, right? So you don't need it really. So you can again write it down in this form. So the next gradient is going to be gradient with respect to hidden state times the gradient of the hidden output with respect to your weight w1, right? And then I can replace whatever I have computed here. So, for this one, I can simply do it because I do have this expression. It's going to be f dot times the gradient of this one, so which is w2. So this is simply that term. And then it's going to remain with this particular expression, right? Then I need to just go ahead and compute that gradient, correct? So I'm going to go ahead and compute that gradient. If I do that, what it's going to be? So let me just write it down for you once again. Oh, no. So maybe here. What is the gradient of ht with respect to w1? So ht, we do know that this guy, maybe I write it here, ht is activated version of w1 times xt. What it would be? It's going to be the gradient of, you do know how to compute this. The gradient of the whole thing, which is f dot of w1 times xt, times the gradient of the argument, which is w1, right? Because that argument, the gradient with respect to w1, sorry, not w1, xt, sorry. It's going to be xt, correct? And then, should I go any further? Do I need to compute any other gradient? No, yeah? So I'm going to stop here, correct? So the thing that is going to happen is that when I just write ht in this form, I could potentially write it down in this form. So I didn't do it there for you because you already see it. But if I am a kind of very, not very intuitive person, I'm going to write down the whole chain rule. I'm going to say the gradient of ht with respect to w1. So ht is a function of w1 and x. So I'm going to compute the gradient with respect to w1, which is the one which we computed on the board, plus the gradient of ht with respect to x times gradient of x with respect to w1, correct? And then if I just replace everything, I'm going to see that this second gradient is 0. And when I just look at the final expression, there is nothing else that I need to compute. So I'm going to stop the chain rule here. So this is where your backpropagation is going to stop. Clear? So now you have the gradient with respect to w1 for rt. and then you can do it for every single time step, and then you sum them up, you subtract it from your weight. You can update W1, correct? So the key point here is that your chain rule in time is going to just go a few steps down in your neural network, and it's going to stop. Yeah? So if I want to have this notation, if we look at the diagram that we had, the gradient when we computed the gradient of r hat t with respect to W1, we're going to just get back propagated to output, then to the previous layer, and we're going to stop. Yeah? And if you want to do it at any particular time, so we just start at the loss at that particular time, and we back propagate toward the hidden layer at that particular time, and then we stop. Clear? And the reason is that every single of them is a decoupled branch, right? The computation that I do at time t does not depend on the computation that I do in time t minus 1. But if I want to use my memory component now, what's going to happen? So if I want to use my memory component, my model is going to look like this one, right? This is the Elman model, meaning that at particular time t, my ht is going to change to this form. So it's going to be W1 times xt. This is what I had in my simple model before. But I do have also plus Wm, the memory weight, times ht minus 1, right? And we can go on with the chain rule once again. Yeah? So if I want to just compute the chain rule once again, I need to do the same thing as we did before. Maybe I take the board again here down. So lots of things are repeating. Oh, no, this is not the one. OK. Sorry. So I can write down the chain rule again, and then I see how long I should go, right? So let's just write it down again. So first, maybe we do the forward pass. So we start with one hidden state h0. We compute we give the first input to our neural network. We compute the first output. Then we go next in time, right? If I go next in time, the thing that is going to happen, the output of the hidden layer at this time is going to carry out to the next time as this state, correct? So that h1 is going to be the input of the next time step. And then x2 is going to also get fed into this neural network, and I compute y2, right? And I keep on going like this towards very end. At one particular time t, I am going to give xt from that time step and the hidden output of the previous time into this hidden layer, and then I compute the r hat, the yt, the output at time t, correct? And now the thing that I want to compute again is this loss, correct? So I want to look at every single time step from t towards 1, and then I compute this loss between the label that I get at time, or the output I get at time t, with the true label that I want, and I want to just compute the gradient to subtract it from my true weight. Okay? Now, let's just go back with this expression as before. So do the same thing as we did in the previous slide once again here. So if I want to compute the gradient with respect to W1, exactly same thing, right? I start with the output. I start from r hat at time t, and I go back towards the output at time t, right? So I'm going to open it up in this form. This is going to be chain rule. Again, I'm going to get from y at time t, output at time t, to the hidden output at time t, right? Because my yt is exactly the same thing. Yt is the same thing as before in terms of ht. And then the gradient of yt with respect to W1 is going to be the same thing, right? So it's going to be the gradient of yt with respect to my hidden state times the gradient of hidden state with respect to W1, correct? So it's going to be the same thing as before. So I can replace this gradient with this expression. If I open it up, really it doesn't matter. But what about the gradient of ht with respect to W1? What should I do? OK, so this is what we did here, right? So we computed the gradient of hidden state with respect to W1, and we stopped at this point, correct? But now, let's write down once again the chain rule together. So look at your hidden state at time t. So your hidden state at time t is W1 times xt plus Wm at times ht minus 1, correct? Right? Now, if I want to write the chain rule, this ht depends on what? It depends on W1 immediately, of course. Yeah? This is one thing that I can write. So I can write gradient with respect to W1 of ht, right? Plus, times, sorry, gradient of W1 with respect to W1. And this guy is simply 1, right? Plus. What is the next thing? It depends on xt as well, right? So I can write down the gradient of ht with respect to xt times gradient of xt with respect to W1. What is this guy? 0. It's 0. OK, I don't need it really. What about the next thing? ht minus 1 is also showing up, right? So I can write it down. OK. Do you see what I'm doing? OK. OK, so it's going to be plus gradient of ht with respect to ht minus 1 times gradient of ht minus 1 time, with respect to W1. Now, is it 0? No. Because ht minus 1 was computed out with x1 out of xt minus 1 and ht minus 2, right? Clear? So if I start opening it up, I have the first term as before, so I want to compute that gradient. I have the second term, which is 0 again as before, but I have this third term. And that gradient of ht minus 1 with respect to W1 is not 0 anymore. Clear?
Well, we had this before, right? We have up until this point, we already calculated that in previous.
Yeah, of course. But if I want to update this, if I want to compute that gradient of r hat t with respect to W1, I don't care if we have computed it. It's OK that we have it. I just want to find out how I can write it down in terms of my previous computations, right?
Then it will be very long because it recursively all the way to h1.
Exactly, exactly. So I just wanted you to see this point. Yeah? OK? So now I need to compute that guy. And as you said, I should go back in time, right? So I should again look at ht minus 1. I would say, OK, it's given in terms of W1 in this form. So again, there are three terms. So one of them is the direct derivative with respect to W1, which is going to show up simply in this form. The other one is the partial derivative with respect to xt minus 1 times the derivative of xt minus 1, which is 0 because that is input, doesn't depend on my weight, which is my data. And the next thing is derivative of ht minus 2 with respect to W1. And this is again not 0, right? So I can keep on going like this. So you can just write it down. You're going to end up in terms of some gradient with respect to a gradient of ht minus 3 with respect to W1, and so on till very end. So what is happening here if you want to just backpropagate at every single time? If I want to backpropagate at a particular time t, I just get back into my hidden layer, but I do not stop. Right? I need to go backward all the way to the beginning of time, right? Because every single of those hidden states, hidden outputs, are impacting my current output. And I just need to look at all of them to know how I should update my W1. This is what I mean by explicitly training my memory. Meaning that I want to know exactly what is the impact of every single previous part of my memory into my current output. Clear? So now this is a kind of, this is a kind of hard story. So I just wanted to tell you where the problem starts. The whole problem starts when you want to update your model. So as you pass through time, at every single time, your memory, even though it is fixed in size, is getting enriched with more and more information, right? Or it's just somehow losing some information of very past and it's adding some new information. But if you want to update your memory weights or any other weights inside your neural network, you should keep looking all the way backward to the very beginning of time. Yeah? And this is quite computationally hard. It's not only about like you cannot do the computation. If the length is not that huge, you can do it computationally, but it's hard to make it work. To make those gradients to be something meaningful.
I may be wrong, but see the equation over there, the last term in the second line, the gradient of h t minus 1, the very last term.
This one.
No, the next one.
This one.
Yes, this one. But isn't that we already compute that in?
Yeah, sure. In that sense that you are saying, this is correct. I do get what you say. You mean that when I am at this time, when I get here, I already know the gradient of this one. Of course, this is how we do it in practice. You're going to see it later. So you're going to start with the very last output, and then you're going to backpropagate all the way here. And then once you are here, you basically have all these single gradients, right? And then you can compute the gradient of every single time step, right?
But if we do dynamic programming from the bottom, if we do in this sequence instead of doing this sequence, then we don't have that much of deep recursion, no?
Yeah, that is not an issue. Your recursion is actually of depth 1 only in time, in this particular architecture. But my issue is not that I cannot compute it. I can compute it. But it's hard to make it work. Meaning that those values that you compute, they can simply vanish or explode. This is going to happen. Okay? And your training is not going to give you any meaningful output.
Oh, I see.
Okay? So it's not, so maybe I didn't make it very clear in my presentation. So I don't simply mean that I cannot do the computation. For the moment, you assume that I can go as far as I want in time. That's fine. The issue is that when I do these computations, at the end of the day, I don't get, you could see that in deep neural network that we had, the gradient simply vanishes. In this case, it could happen even worse. Yes?
Sorry,
it's
so
only.
that the last term will essentially be 0 because the gradient vanishes. The gradient of ht minus 1 with respect to W1 will vanish.
It could potentially vanish, and then its impact on your training at time t is going to vanish as well. And it doesn't mean that you don't have gradient, like in deep neural network. You do have gradient, but that gradient doesn't go backward all the way in time, meaning that you don't, at the end of the day, you don't really learn to, or you don't train your network to learn from something far away in time.
I see.
Okay?
Makes sense to me now.
Yes? Yeah.
Can't we use what we've seen last period with
The skip connection? Yeah, we're going to do something like that, but it's a bit different. The idea is gating, but this is pretty much the same thing, right? Yeah. Yes?
I don't think dynamic programming solves this issue. This issue cannot be solved by dynamic. This is not executed symbolically, so you can know the symbolic value of W1, the derivative of ht minus 1 against W1, but without knowing all those values with t inside, you cannot evaluate the value of this. So the only way to do it is actually recursive.
Yeah, recursion, yeah. I'm not sure if by dynamic programming he meant he's going to find the kind of converging state in a finite fashion. No, it doesn't mean that. Yeah, at the end of the day, what you're going to do, as I told you, you start from very last time interval. You just backpropagate all the way to the beginning, and at this point, you can compute every gradient towards the output.
Yeah, I totally agree with that. The
Yeah.
problem is I just want to clarify, there is no way for you to do it from the lower
No, you cannot do it. But once you start from very last time interval, you really don't need at every single time to repeat the backpropagation all the way. So you just need to backpropagate from very last time to the very first time once, and then you can compute everything. So the only extra depth is in time. Yeah, that is correct, yes. But at the end of the day, I mean, say you can do it, it's not a huge thing. I mean, we can train deep networks with 1,000 layers. So it means that we can potentially have thousands of time frames, right? But the issue is that at the end of the day, what you train at the very end is not going to really depend on your input at the very, very beginning, right? So, and this is something that you were trying to avoid, yeah? You wanted to carry all the information from the beginning towards the end. So, yeah, as I told you, so this is the issue that we have. We need to train architecture through time, and this is going to be a very, very challenging thing. Now, you might ask me, did Elman really do that? No, he didn't. What he did actually, he actually truncated at that particular time. So he basically did what we did for non-recursive model, okay? So when he got into this point, when he wanted to compute this guy, the gradient of ht minus 1 with respect to w1, he said that, okay, I cannot go, I mean, in 1990, you can guess there was no enough computation. So he said this is approximately 0. And this is what I mean that he didn't explicitly learn to remember. What he did, he just accumulated this state and just feed it into the current output, but he didn't go back in time to just correct all the weights. And this is not really the thing that we are looking for, right? So he didn't do that. He did just this simple thing, and this is why I was telling you all the time that he was just learning the memory implicitly, not explicitly. So yeah, this is, yeah, okay. Okay, maybe I just keep with this one for the next session on Thursday. I'm going to just, let me finish this one. So I hope that you got the idea, the challenge that we have in RNN. So we need to just go backward through the whole time. I'm going to start from this one again on Thursday. And then there is just a few slides on this guy. And then we're going to start with a real recurrent neural network. We see how we can move forward and backward. The backward is pretty much the same thing. But then we need to just write everything that we did here in algorithmic form. Yeah? And then we're going to see the issue, this vanishing gradient, and how we can deal with that, which is the idea of gating. Okay? So I think it was a bit faster than usual today, but I guess, I mean, most of the things that I did today are clear for you. I didn't want you to have like too many details for this part because it's introductory, but we're going to do it more details next time. Okay? So see you on